All right, it's officially 1300 hours, so let's get going. So the plan for today is that I just carry on from where I left you virtually in the videos. I don't know if all of you had a look at the videos. I mean, if you didn't look at the videos, then it's kind of okay to read the book or the notes. You get most of the gist of the whole thing. I mean, I've got an ambitious plan for today because I'd like to bulldoze all the way through electrostatics in matter so that next week we can move on to magnetostatics. So what I hope again is that this is a bit of a refresher for you of things that you've already at least partly seen. Maybe it's a revisitation in more detail of things you already know. But before I get going to this, I just had a question from one of you about the midterm exam. There was a question last time about whether the midterm could count positively for you. That is, at the final, you'll sit the final. You have no choice on that one. But then the grades you would have accumulated in the midterm would count for your final grade only if they contributed positively to this. So I'm kind of sympathetic to this idea because, midterm, it's an occasion for us to get to know each other and, kind of useful thing. So I'm actually happy to do that. The other reason why I'm happy to do that is because at the final, the subject matter for the final exam will, of course, contain all the course. So in a sense, I'm ready to stand by the final exam that I will write as the single point of assessment as whether you know your stuff or not. So, unless there are protests from your end, then the midterm will count for your final grade if it contributes positively. Otherwise, it's going to be just the final. Is anybody in disagreement with this or really protesting? I mean, I expect to receive bricks and, shouts and I don't know. So you're okay with that? Yeah, it's fine. Okay. The assistants have told me that, yeah, question?
Well, about that midterm, do you already know a certain location for people who has the black hole exam?
Yeah, so I'm working on an alternate location in Science Park for those for whom this will be a problem. And I still don't have the final location for this. But the strategy I'm pursuing is that the main one is going to be in the normal place, the fashion center. So I'll try to get a room in Science Park for as many people as I can, and then those who will want to make use of that alternate room will have to show me that they're registered to this other exam thing, and that they can just go to Science Park. So I mean, give me another week, and then I'll get back to you on this. I mean, it's not forgotten. You have to learn with me. Things happen, like just-in-time manufacturing, and you will get the information hopefully by next week. Yeah. Once I get the room. Booking rooms in Science Park is like an interesting, unsolvable problem. So we'll see. But I am confident that that's going to work out. So that's going to be the solution, actually. At the same time, the exam, but just two separate locations. One bulk, one secondary. Yeah. Okay? Okay. The assistants were telling me that not everybody shows up at the exercise session. So you're adults. You can determine for yourself how best you study, how best you work. In a sense, if one assistant is busy only with 3 students, then it's great for the 3 students who have the full attention of the assistant. If you're in a werkcollege which is perhaps better attended, you could consider going to this other werkcollege which is less attended. You can ask your colleagues. I'm kind of flexible about that. Yeah, we're not taking, photo recognition patterns of your face as you walk in, so we don't police you on this. So I really leave it up to you. However, I really do expect you to be able to do the stuff which is written in the notes. So if you come at the exam and you haven't sufficiently prepared, I mean, you will feel it, physically. Yeah? So I really urge you to not postpone your diving into the subject matter and maybe correcting the stuff that you don't really control very well until the last minute, because experience shows that this doesn't work. And the thing I'd like to tell you to motivate you is that if you're going to do this for one particular course, then let it be electrodynamics, because this is stuff that will impact long-term your life, your vision of everything and whatnot. Okay, it's really worth investing time in there. So please make sure that you kind of try to keep up, because otherwise you're kind of missing out on this stuff. Okay, so once again, this is up to you. You don't have to show up to the lecture. If you just are happy with the videos, that's all fine. I've had plenty of students in the past that actually never attended my lectures, just listened to the videos in like accelerated fashion, and that was good enough. Fine, I've got no problem with that. But of course, if you don't participate in the exercises, don't come to the lectures, and then ask me what Gauss's law is after the final exam, then don't expect a passing grade from me, all right? Because it's my job to police that if we release you in the wild, and if a company hires you and asks you to compute certain things, that your computations don't lead to disaster, disease, death, and things like that. Okay, so please take it seriously. Okay. So, the assistants also during the exercise sessions, they can help you out with stuff that you might not have completely understood from the lectures and things like that. So, we'll see how you do. Okay. And for the midterm exam, again, we'll see a bit how we do. I want to include at least magnetostatics in the midterm. And then once again, the final will contain everything that we will have seen, hopefully stuff including lots of interesting dynamics, in the second half of the course. Okay. So let's get going. I put up the notes also for today online just earlier today. So once again, these are the notes that I'm actually using to teach you. You can refer to them to check the equations and the content. Some of the stuff that I wrote in there, I'm actually not going to talk about very long here. I'm going to do a kind of selection of the important things in there. But this is about electrostatics in matter. Okay? So, the discussion in the book, in Griffiths, actually starts from the right things. It starts from the fundamental things. So it starts with a little discussion of how electric fields influence fundamental particles. Now, of course, this is something which is quite complicated, right? So an electron, if you put it in an electric field, will act in a certain way. In order to really, really understand that in detail, you need quantum electrodynamics, relativistic quantum electrodynamics, and this is not what this course is about. So like in Griffiths, we will make the assumption that the particles we deal with are kind of fundamental, unaltered by the presence of this electrical field. But when you start looking at slightly more complicated objects like atoms, say the hydrogen atom, proton, electron around it, electron orbits around, cloud, essentially you can already start understanding that certain things can happen if you've got some electrical field. Okay, so we've got our model for the atom, a positive nucleus somewhere, and we've got a cloud representing the wave function of the electron. And you see here we've got like a non-rotationally symmetric electrical field. No, this is meant to be a nice little circle. So that's the negative charge that contains this cloud. Of course, if the electron is in its ground state, it's got this S wave, spherically symmetric. So if you look at this object from a certain distance, it just looks like a neutral thing. Yeah, in the absence of a field, it's just plus charge, minus charge, canceling each other. You don't see anything. However, if you put this object into an electrical field, then of course what's going to happen is that there's going to be a displacement of one thing with respect to the other. So the positive and the negative, they would suddenly split a bit away from each other. And what you would expect is that from a certain distance, this starts looking like a dipole, like an electric dipole, because there's a little bit of distance between the two center of charges of the positive and the negative. Now, I'm not going to write very complicated equations here. We could start from the Schrödinger equation for the hydrogen atom, put the perturbation of the electrical field in there, solve for everything, compute the polarization of it. So what we would get is something that we can already predict with our nose. We can predict that the dipole moment that we would get from such a thing would be something proportional to the electric field itself. Okay, so why do we expect that in general? It's a very general principle, if you want, in physics in the vicinity of equilibrium. It's called Le Chatelier's principle. I don't know if you've come across this. So what's the characteristic of an equilibrium? An equilibrium is, if you want, if you plot a potential, you're sitting at the bottom of a potential, okay? And you're sitting at the minimum of the effective energy of this. So what's a minimum? It's a place where the derivative is zero, okay? Now, if you put a perturbation onto this, a small perturbation, typically what you will do is that you will displace the minimum with something linearly proportional to the perturbation that you're putting in there. Okay, so this is really what this means here. So there's an equilibrium position where the electronic cloud is centered on the position of the proton. But if you put a little perturbation, then the displacement you will get will be proportional to this perturbation. And this works for small perturbations. And this is really just a consequence of the fact that you've got some potential minimum represented by some positive curvature. Okay, so again, this is not exam material, it's just stuff you should know. It works for almost everything in the vicinity of equilibrium. Okay, so a single atom will essentially develop a certain dipole moment when subjected to this electric field from outside. There are lots of other more complicated examples. You can look at molecules. You can look at CO2, H2O, whatever. They have different geometries. So CO2 is on a line. H2O has this angle of 105 degrees. And of course, the charge distribution within these is not uniform. Okay, so H2O, for example, right? It has this nice little triangle. So if you put that in an electric field, of course, it will line up in a certain way. It might even deform a bit if your field is strong enough. But the important thing is that, essentially, if you had like a collection of these atoms in a thermal bath, and you would put an electrical field onto that, there would, on average, be a kind of dipole moment accumulation proportional to the field that would show up. Okay? So, I could give a whole course about quantum mechanical explanations of how you calculate that, how you actually do this. That's not the point here. The point I want to make is that it's quite natural for neutral matter composed of fundamental constituents to polarize when you subject it to electrical fields. Okay, so it works for molecules, works for liquids, gases, whatever. Now, of course, the degree to which things polarize greatly depends on the fundamentals of that thing. So this little coefficient here, we're not saying what it is different for every type of atom, for every type of molecule, for every type of, compound you will look at. Okay, but in general, the linearity of it will be quite robust. Okay, so there are situations where actually you don't have this, okay? This is the normal, like, equilibrium situations. So, like if you want less normal cases, in less normal cases, you could, for example, have that the polarization is different than zero, even if the electrical field is equal to zero. Okay, and if you have a piece of matter that does that, that's called an electret. Okay, it's very rare, but there are some compounds that show this property. It's, if you want, the electric equivalent of a bar magnet. Okay, you can have nonlinear dielectrics. Okay, and by the way, a dielectric is just a piece of matter that responds to electrical field by polarizing. Okay, so you can have a nonlinear dielectric. Again, these are not equations that I expect you to know at all. What that means here is that if you want the polarization that you get, or the moment that you get, has a term which is proportional to E, and it could be a different vector. Let me keep it simple here. So let's say it's the same. But then you could have something that has to do with E cubed. And then you would have indices, alpha, beta, gamma, with some tensors here. Things. Okay? So you can understand why there are terms like that, because of course, say I take my hydrogen atom and I start putting the field stronger and stronger and stronger. Of course, at first it's proportional to the electrical field, but at some point maybe some other physics is going to start taking over, and then there would be higher order corrections. But again, this is stuff you can completely safely forget about. Okay, so we'll focus on the linear case here. Okay, so let's just discuss a little bit how we want to treat this. And the start of the discussion really considers an object, a macroscopic object, in which we will try to characterize the degree of polarization in it. Okay, so this is a discussion that in the book is referred to as the field of a polarized object. Okay, and the fundamental quantity that we will consider is this P capital, yeah, so this is like a capital P, which is by definition the dipole moment per unit volume. Okay, so this is called the polarization, and it's a very, very important object for everything we're going to do in matter. Okay, so polarization. So you see, unfortunately, in physics, we use the same words to mean completely different things. So this has got nothing to do with, polarization of light or anything like that. This is only spatial distribution of positive versus negative charges. Okay, and it's just essentially the dipole moment, like you've seen in the multipole expansion, but now measured per unit volume. So when we integrate over the whole volume of the material, we will have the total polarization of the object. Okay, so let's say that we have a single dipole. Okay, so for a single dipole, we already know what the potential is. Okay, we've seen that before. So if I have a single dipole at at position r prime, then the potential at r is just 1 over 4 pi epsilon 0, and the quantity that I have, r minus r prime, dotted into the dipole moment, divided by distance cubed. Okay, so once again, the potential is just the dipole moment. You remember the dipole moment? It's just like the sum of the distances with charge. And then you dot that into the distance. And the potential of a dipole falls off as 1 over r squared. Okay? And you remember once again why this is the case. Dipole is a neutral object, so the monopole term vanishes. The 1 over r term vanishes. The first term that you see is the first correction to this, which falls like 1 over r squared. And of course, the potential is proportional to the value of the dipole moment with then this dot into the thing. Okay, so you see that's one very important thing. The interaction that you have with the dipole is not the same depending on the direction that you have with respect to the dipole. Okay, there's a vector. Sorry, is it readable or?
It's a minus, right?
Yeah, that's a minus. Yeah, maybe I can try to. There's this little glitch here. Eh? Let's do microscopics here. Yeah, I'll rewrite the minus. I mean, it was minus trying to get a plus, but not quite making it. Okay? So that's the potential you would get from a single dipole. Now, of course, if you have a polarization in the bulk, because of linearity, we know that we can compute the potential by just integrating over the distribution of all these dipole moments that we have, yeah, per unit volume. So if we have electricity here, yes. Okay, so for spatial distribution, yeah. so represented by polarization P, then the potential at R is just 1 over 4 pi epsilon 0. And now I just need to integrate this over the volume over which my dipoles are distributed. Okay, so V is again the volume over which my polarization is non-zero. And then I just have the same thing, R minus R prime. And now I dot this into the polarization per unit volume divided by R minus R prime cubed. Okay, it's as simple as this. So you know, you got your piece of matter, it's made of little atoms, and all these things have a little dipole moment, and per unit volume, on average, you describe that by this big vector-valued function of position in 3D. And the total potential that you get is given by the simple linearization of the single dipole expression here. You integrate over your whole distribution here. Okay? So this equation, there's nothing wrong with it, but there's something nice that we can do with it to make it a little bit more enlightening. Okay? So, a more enlightening Is it okay? Or I see people suffering greatly because of my handwriting, but you know, you have my sympathy. But yeah, that's the way it is.
In the formula for potential, the capital P.
So this one here is the capital P. This one, huh? Because this capital P, right? So you have to visualize what it is, right? It's like the physical density of dipoles. All the dipoles summed together as vectors, right? So you'd like split your volume. You'd have your d tau prime unit volume here, and you'd split it up in little cells, and then you add all the dipoles in these little cells as vectors, you know, so they point like this, but in total it's like one vector like this, and then you sum that everywhere. That's what this means. Okay? Yes?
Maybe making a small doodle would help.
I'm sorry?
A small doodle drawing.
Drawing. I mean, you asked for it, right? So, okay, so let's let me make space for the little drawing. There's a lot of space. That'll be a little drawing. Okay, so what do I mean by this? So let's imagine that we look at a chunk of matter. Here's a chunk of matter. Okay, and this is a bulk chunk of matter, 10 to the 23 atoms. Okay, but I can look at it with a microscope. And I look at it with a microscope, I start seeing little chunks here in which there are, say, 10 to the 16 atoms. Okay, and these things here, if I just had this little chunk here, there would be, you know, inside there would be a huge distribution of atoms. And these are strange atoms because they're a little bit polarized. It's like water molecules. Okay, water molecules plus minus is a bit, you know, asymmetrically distributed. But these little molecules, you know, so let's say I've got a plus here, minus here, plus here, minus here. Each of these molecules has a little dipole moment. Okay? So the little arrows are the dipole moment. It's even like it's wanting to be big here. But what I do is within this cell here, I am adding as vectors all these microscopic dipole moments. Okay? And that gives me one big arrow. And this big arrow, divided by the unit volume that I have here, is the polarization at that point. Okay? So the fact that I've got many, many atoms here means that just by the central limit theorem, I expect to get a well-defined average with very narrow distribution. So the polarization vector itself is well-defined and presumably smooth as I move within the material. Okay? Does this drawing help in any way? It's a miracle if it does, but...
I think the drawing helps, but if I'm correct here, effectively we're just saying there are so many atoms that instead of using a summation sign, we're just using an integral, right?
Yeah. It's what we're doing actually. So the true thing that we're doing is we're doing a summation. We are actually summing every single little source of polarization there is, be that the fundamental molecules that this thing is made of. However, because we're doing a summation over so many different constituents, there is a notion that we can replace the value by a kind of average value, right? Central limit theorem. If I have things with a distribution of probability, so my water molecules, they have a distribution of probability for the direction that they have, okay? And if I have just water without any kind of force, any field going through it, then you expect the distribution of the orientations of the molecules to be completely random. Therefore, you expect the material to be unpolarized, because any direction locally is as likely as any other. The average is 0, and so the total moment would be moment of one molecule times number of molecules. But the fluctuations that you would have around the average would go like the square root of the number of molecules. Therefore, the total thing, scaled by the fluctuations scale to 0 relative to the average, which means that the average, you can replace it by a single number if you want. You don't need to take into account the fluctuations. So this considers that when you write P here at point R, there are so many contributions in there that you don't need to take into account the local fluctuations in P of R. Okay, that's the kind of approximation that we make. So we're doing as if matter was a continuous thing with no microscopics whatsoever. That's what people thought in the days of Maxwell anyway. Okay, so these things would be completely smooth. Now we know better, of course. We know that if we were to look inside the piece of matter, there would be dramatic fluctuations in the values of the electrical fields and the orientations of the molecules. But nonetheless, when we step away and look at collections of these molecules, then we see averages that do not fluctuate. And this is what this represents. Okay? There was another question at the back? Yeah.
But then you have to zoom in at some point that the dipole moment wouldn't be 0, because else how deeply you have to zoom in.
I should be careful in the examples I give you. So if I give you just a gas of water molecules in the absence of an external field, then the orientation of each molecule is completely random. And you will have order 10 to the 23 molecules. And if I ask you to compute the total, so each molecule has its dipole moment, sum that over all molecules. What you will get is 0, because all the orientations are equally probable. However, if I ask you, what's the average if this gas of molecules is now in a little electrical field? Because of the presence of the little electrical field, there is now a higher probability for your molecules to align their dipole moment like against the field than with it. So therefore, now your average that you compute attains a non-zero value. In fact, if I tell you that the field is of order of 1, then the total dipole moment that you will get is dipole moment of a single molecule times 10 to the 23 times a factor of 1. Okay? And you're then free to replace that thing with something smooth, because I'm telling you, okay, I don't care if it's 10 to the 23 or 10 to the 23 plus 1. In fact, what I tell you is that I only care if it's 10 to the 23, I expect that per unit volume, you see, that's why we do per unit volume, because per unit volume you also have of order 10 to the 23. So then you divide by the unit volume, you get some number of moment per unit volume. And then the fluctuations of that we might be worried about, then they will be of order, 10 to the 11, 12 divided by 10 to the 23. So you absolutely don't care about it. You see this, the corrections to this, if I give you a smooth function of polarization through the material, you know that you can expect this to be accurate to about 10 digits if you want, before you start seeing fluctuations in there. So if you want to start seeing fluctuations, you need to go to very few particles, and then the central limit theorem doesn't work. But here we're doing everything macroscopic. Okay? Does that kind of help a bit, or yeah? Okay, so that's the idea with these things. Okay, so let's see where we were. So just going back to our more enlightening version here, let me just displace that back here. So what we just wrote, once again, is completely correct mathematically, but we're just going to use a little trick here. Okay? We're going to use the fact that, just a little mathematical identity, we're going to use the identity that if I take the gradient with respect to the prime coordinate of 1 over r minus r prime, then this is just the expression that I have here, right? It's r over r cubed. Okay, this is just an identity that you can verify for yourself. It's rather simple. Okay, so understand what I mean, right? So if I write, like grad prime, I mean d with respect to the primed coordinates. Okay? And we're also going to use one of the vector identities that we had. So the vector identity that we'll use is that the divergence of the product of a scalar function with a vector function like this. You see, again, it's a bit like the chain rule. You see it feels quite natural. So if you do the derivative on the a, then this is going to be f times the divergence of a. And these are vectors, right? Plus just a dotted into the gradient of f. Okay, so this is just an identity. Again, I wouldn't expect you to know this by heart, but quite frankly, I think you can get used to it quite easily. So we'll just use it for a trick. Okay, so let's just rewrite our potential at r as the following thing. What I'm going to do is I'll just rewrite the identity. So we had 4 pi epsilon 0, the integral over our volume. Okay, and now I had this r over r cubed, but now I'm just going to write this as the gradient here. So let me write, I can change the order here, so that's my polarization at r prime. And now I'm going to dot this into the gradient of r minus r prime. Okay, I've just substituted that identity here in our earlier formula. Now, what I'm going to do is I'm going to use this identity here. You see here what I have is the equivalent of the a dot grad f. Okay, so this is a and then grad f. F is just 1 over r. So I get 2 terms. I get the equivalent of this term minus this term here. So what does that give me? 1 over 4 pi epsilon 0. Now I still do, well, let me factorize that out completely. I do the integral over my volume, d tau prime. And now I will just have, this expression here. So the divergence with respect to prime coordinates of the product of f times a, and f times a is just p of r prime divided by r minus r prime. Okay? And then I have minus, this term going on the other side. So that's the integral over my volume, again, d tau prime, of now 1 over r minus r prime, with the primed gradient, prime divergence applied on P at R prime. Okay, so you'll see in a minute why this is interesting to do. Okay, so we can, in this term here, we can use the divergence theorem. Okay, we've got a volume integral of a divergence like this, and you know that this becomes the surface integral of the unit vector on the surface with the surface element. Okay, so we're just going to rewrite this whole thing. So V of R just becomes 1 over 4 pi epsilon 0. And now the integral over, so the closed integral over the surface of the volume. Okay, and I will write the surface integral as usual in terms of surface element dA prime, and then dotted into this vector here. So P of R prime divided by R minus R prime. Okay, and then I just have the other term here, which is the same as above. Okay, and that's the bit where we come to the interpretation of it. So the first term, well, first of all, both terms just have the 1 over distance function, okay? And you remember, you know, so the potential goes like 1 over R. So here in, maybe let me start with this term here. You remember the expression that we had for the potential. The potential was just 1 over 4 pi epsilon 0 integral over the volume of charge density divided by R minus R prime. Okay? So we're not doing anything different here. It's exactly the same formula, except that now what we do is that we interpret minus divergence of P as a bulk charge density. Okay, so what we'll do is that we will define a rho B of R as minus the divergence of P at R. Okay? So this is like a bulk charge density. And similarly, if we look at this one here, we can interpret this as like a surface charge distribution. And the charge at the surface is just given by the dot of this into the unit normal. Okay, so let me just write it and then you'll see. So this is just the polarization vector at R, dotted into the unit vector at the surface, right? So n is unit vector unit vector. Well, I can just write above it. Okay, so let me just rewrite and then interpret a bit. So we get the cleaner version that V at a certain point R has two contributions. It has the surface contribution integral over the surface dA prime dotted into the sigma b. Actually, I should just write. I shouldn't even write the dot. It's not a dot thing. Let me just write it. R prime divided by R minus R prime. And then it has the volume 1 over 4 pi epsilon 0 integral over the volume d tau prime and the rho bulk of R prime divided by R minus R prime. And let me just clean up the notations. So the previous yeah, so I just want to have the same notations for my surface as I used to have. Yeah, okay, so in the past I was just, yeah, so here to map with the earlier notation. So this is just a scalar here, right? So I'm not going to do this. Okay, so what does it mean? Let's just do another drawing, okay, to explain the first term. So let's imagine that I have, or maybe what's the easiest? Maybe I can start with this. So I have a certain volume, okay, and in this volume I have a polarization vector P. Okay? Now, if I look at the bulk here, let me kind of look inside the bulk here. So I have like a magnification of what happens here. Then what do I have? I have my polarization vector, but if I were to have a spatial dependence of my polarization vector, then that would mean something. So I could imagine that I have my my little polarization vectors, say like this, but then as I move out, maybe they become like longer. Okay, so I'm trying to explain this term here as I go. Okay, you'll need a stretch of the imagination to make it out from this thing, but what do I mean here? Okay, so let's just imagine looking at a little piece of the volume here. If I tell you that the polarization has absolutely no spatial dependence whatsoever, then what it means as I move around is that there's no need to like add charge because these are dipole moments, right? So they're neutral. So if my polarization has no spatial dependence, then every single little positive charge you'll have will be compensated by the little negative of the other dipole on the side, and they kind of all cancel each other. Okay, because if I were to put, say, let's do like a 1D example. So if I have a little dipole like this that has minus plus here, and then I put another minus plus, I put another minus plus, I put another minus plus, all uniformly like this as I go along. Then as I average out, you see this bit is like neutral. Okay? So if there is absolutely no spatial dependence to the density of plus and minus, then the thing looks like just a uniform neutral charge. Okay? But maybe it's even easier to start with the surface term here. But you see now, the only place where the charges are like not compensated would be at the boundary. Okay, so that's the surface charge that you have here. Now for the bulk charge here, I could imagine that as I move along, suddenly I start having, maybe more, slightly bigger, and then more plus charge if you represent my drawing. Okay? So what I mean by that is that suddenly the dipoles become stronger and stronger as I move. But that means essentially that there's a slightly faster increase of the positive versus the negative as I displace. And to do that, I need to put charge. Do you kind of see what I'm getting at? Do you visualize it? So the dipoles individually, they're neutral. But if the density of the dipoles varies in space, that means that locally, at the point where the dipole moment increases, I need to have a bit more positive charge. Okay? And that is this object here. Okay, so if you want, these bound charges here, they represent the spatial variation in the polarization. And then whatever is not compensated at the boundary is picked up by this boundary charge here. Okay? Yeah, question?
You draw the arrows bigger as further away they go from the center.
Yeah, so in
Because there's a positive charge on the surface.
So in this case here, what I'm imagining is that I take a point inside the material, and as I move away from that point, I notice that the local dipole moments become bigger, just as a kind of illustrative thing. And if you want, that means that so if I look at the way this looks from outside, I see lots of positive and negative charges. But because the dipole moments increase as I move out, if you want, it's as if I had an accumulation of charge there, because the dipoles don't cancel each other as I move out. And this becomes completely equivalent, as far as the potential is concerned, to just having a charge density given by the divergence of the polarization. So if polarization has no spatial dependence, nothing happens. But if the polarization changes, then it's completely equivalent as having a local charge in there. Okay, I think maybe just doing little drawings is going to help out. I mean, the drawings in the book are much better than mine, and they're more illustrative. There are just two. You just need the one with the divergence, and then the one with the surface. And the one with the surface is easier to understand. So let me imagine that my dipoles, I've got the positive charges and the negative charges. I've got my object, and I just shift one with respect to the other. You see, so if they're exactly on top of each other, all the charges are exactly canceled. But if I shift them a little bit with respect to each other, then in the bulk, the charges are still completely canceled. But at the boundary, where I've done the shift, and there's just a little boundary place where it's not canceled. And that's the surface charge that gets induced. Okay? So this is just giving you the equivalent formulation of the expression for the potential. Yeah, and you'll find that in. So what's the idea? The idea is that if I have an object with internal polarization, then its potential is absolutely equivalent to another object that has a surface charge and a bulk charge distribution. Yeah, so fields of dipoles, they look like just accumulated independent charges. Question?
Yeah, I don't quite understand where the sigma equation is coming from. The second one.
This one here.
No, above the sigma equation, P relative to the.
This one here.
Yeah.
So let's step back. So okay. So once again, so we just use the identity to rewrite this like this because we had this P dotted into R over R cubed, and then I just use this first identity to rewrite this, and now I use this vector calculus identity to rewrite this thing into two different terms, right? So P is A in this notation, and F is just 1 over R minus R prime. And now I get two terms, right? Because this term is just this term here. So then this integral is just the integral of this minus this. So The first term is this divergence of the P over R. And now, because I'm doing a bulk integral with the divergence, I can use the divergence theorem telling me that the integral of the divergence of an object over a volume is the integral on the surface of the object dotted into the unit normal vector. So it's just the divergence theorem, Gauss's theorem if you prefer, or Green's theorem if you even prefer. Yeah. So that's the idea. Okay. So we're not playing any like black magic here or anything. We're using a mathematical identity to reinterpret the fields coming from polarized objects as fields coming from, if you want, unpolarized objects, but with bulk and charge distributions. And that's a useful visualization. Actually, physically, this really corresponds to more or less what you would see from a distance anyway. If you do have a set of dipoles per unit volume, in the end, what you see is like uncompensated charges from them. Okay, and then it's completely equivalent. Okay, so that's just the expression for this. So maybe we take a little break and we do a little example with that later, and I can maybe